They put out a poll saying, hey, this guy's up this percentage, this guy's up this percentage. How do they get that information? Take a guess. No guesses? No, polling before the vote. Yeah, before the vote. In the weeks and months leading up to the election, polls come out saying this guy's up by this. How do they get that information? How do they know? If I'm working for a polling company and my job is to go out and get that data so I can give it to the news organizations to disseminate, how do I get that data?
They call people?
Yes, they call people. Question, if you get a phone call from a number that you don't recognize, how often do you pick it up?
Not super often.
Not super often. See, 20 years ago, when they were calling people to take surveys, they didn't have not everyone had caller ID, so they'd call the landline, you'd be like, I don't know who this is, click hello, and then you would find out who it was, and then you would decide whether or not you wanted to take the survey. Nowadays, in the year 2020, they still do that. They still call people, except how many people have landlines? Not many. So they're calling your cell phones. And if they're calling your cell phones, everybody's got caller ID. Everybody knows what phone number. Doesn't it, oh, speaking of phone calls, when you get a phone call, does it say what state it's calling from? Yeah. Oh, that's not New Jersey. I'm not picking that up. Who's in trouble? Mr. Marcus' room. Hey. I gotcha. I appreciate that. Thank you. No worries. I will. Bye-bye. That was weird. Anyway, back to this. So my point is this. If you get a poll, you have to poll about 1,000 people in order to get accurate results. If you poll about 1,000 people, not everyone's going to answer their phones and not everyone's going to agree to take your survey. If you want to poll 1,000 people, you have to poll, I am not even kidding you, probably about 200,000 people just to get about 1,000 responses. You would have to poll over 200,000 people just to get 1,000 responses. That does not seem very cost effective to me. See, what ends up happening is the polls that are put out nowadays are off. For example, I'll give you one great example. Florida. Florida went to Trump during the election. Do you know how many points Biden was in the lead by in the polls? He was up by 4 or 5 points. Biden was up by 4 or 5 points in Florida, according to the polls. But then when the election showed up, Trump ended up winning it by like 2 or 3. How did that happen? The polls are wrong. No, the polls are not wrong. The way in which they collect the data is wrong. Ooh, I'm going to fix it. I'm going to fix it one day. Just you wait and see. I don't care. I really don't care. I want to get started with what I'm doing. Okay. Today, this week, is the last week of the first marking period. If there are things that you owe me, you need to get on top of those things. For the most part, I don't know. I'll have to wait and see. I don't know what you guys have done individually. But next week begins the second marking period. Next week begins 5 days a week. I'm so pumped and excited. Now, I showed this during the Virtual Friday, the week before we left for that week off. But I'll bring it up again because not everyone saw it. Come on, you. There we go. Flip. There we go. I don't know if anyone has seen this or not, but this is going to be the schedule next week. Starting Monday, they're going back to 5 days, and this is what it's going to look like for the time being. Will they change it eventually? I don't know. But basically, you show up for homeroom as normal, but homeroom will be over at 7:20, and then you'll have first period. First period to be an hour. 4-minute passing time, class for an hour. 4-minute passing time, class for an hour. That would be us, third period. 4-minute passing time, class for about an hour and 8 minutes. That'd be fourth period. And then you go home at 11:40. Then there's about a 40-minute lunch for teachers, and you guys all do your thing, get home. Then there's this afternoon schedule. Now, this afternoon schedule in gray, that's all on me. Everything in gray, I am going to be responsible for during my afternoon sessions here in the building. On Tuesdays and Fridays, they are going to have their we're going to have our virtual meetings, except those virtual meetings are 100% optional. They even say it right here. Please think of Tuesday, Friday virtual meets as office hours where students can check in and ask questions, because each virtual meet only lasts about 10 minutes. It's going to be chaos. This schedule is probably going to fall apart. I'm just giving you the heads up.
Is homeroom still first period, or is it the second?
Same. Yes. You'll be there. You know how like homeroom goes to 7:25? It'll now go to 7:20, but it'll still be your first period class. Yeah. Fun! I don't know. I don't care. But this is the way that things are kind of going now. Again, will it stay this way? I don't know. I have no clue. Do you know how many teachers in this building are quarantining for like 2 weeks right now? There's at least like a half a dozen teachers quarantining for 2 weeks because they went away on vacation during the week off. I just got an email from the principal, probably the end of yesterday, where 30 extra kids were moving to virtual. Anyway, this is going to be fun. Ladies and gentlemen, here's what I want to do. I want to introduce the next chapter. In order to do that, I want to do it with a flourish. But before I introduce it with a flourish, I'm going to need those notebooks out and open. Let's do it. I'm so pumped. Let's see here. Desmos. Great calculator. Here. Japan. The pumpkins on my front porch are starting to disintegrate. So my wife sent me this. You can't see it. Where is it? My wife sent me this picture of our pumpkins on our front porch. You can see the one in the middle that's like disintegrating. You can't see it, but she had put little sticks in them with little messages for people showing up to our house, which I thought was really funny. Basically for people delivering things. But it's just, I don't know. So she texts me and she's just like, hey, this took me probably about a half an hour to do. Could you clean these up when you get home? I'm like, why did you not do them? Anyway, back to this. Desmos. There we go. This is the quadratic that we have been dealing with for the past 2 months. We have been looking at the graphs of these quadratics, identifying the vertices of this quadratic, or the vertex of this quadratic, identifying the x-intercepts of this quadratic, factoring this quadratic, solving this quadratic, doing a lot of different things with this quadratic. This is just one example of the quadratics that we've been faced with. Algebra 2 mainly starts off with just focusing on quadratics. And the skills that we have been going over the past 2 months are going to play a role in this new unit. Algebra 1 was mainly about linear functions, straight lines. Algebra 2 has started off with these weird-looking quadratics, these parabola-shaped things. But now we are taking a step in a new direction. And that new direction, let's just try something out like this. Let me try this example, and then I can maneuver around this a little bit. Let's try. Nope, not that one. Let's change that to a minus. There we go. There's a good one. This is a perfect example of a cubic equation. When we were dealing with quadratics, those were what we called second-degree polynomials. We referred to them as second-degree polynomials because something like y equals x squared plus x minus 6 right there had a largest exponent of 2. But this example that you see on Desmos now is your first step into what we call third-degree polynomials. Third-degree polynomials do not act in the same manner that second-degree polynomials do. Second-degree polynomials are quadratics. They are parabolic. They either open up or they open down. These things do whatever the heck they want. But they still follow a certain set of rules that we are going to deep dive into. Now, beyond third-degree polynomials, I could also talk about maybe something like this. Let's zoom in there. Actually, you know, I'm going to move that one down a little. Let's do it here. Yep, there we go. Look at that one. This is an example of a fourth-degree polynomial. They don't always have this shape. In fact, you know what? I'm going to add more stuff to it. Just for the fun of it. The reason why it is a fourth-degree polynomial. Look at that. Yeah, the reason why it's a fourth-degree polynomial is because of the largest exponent that is in the graph or in the equation. Fourth-degree polynomial. Question. How many times does this graph cross the x-axis? 4 times. It's insane. What the heck? 4 times. They won't always cross 4 times. Watch this. I can make it cross less. Watch, I'll make it cross less. There you go. This one only crosses 2 times. This one, hold on, watch this. This one crosses 0 times. But it's still a fourth-degree polynomial. Hold on, let me see if I can do something crazy here. Hold on. Let's try a 5th degree. No, okay, here, hold on. I can do a 5th degree. So no, get away, you. We'll do that. Plus 2x to the 4th minus x to the 3rd. I'm literally making this up as I go along. Plus x squared minus 4x. 4x plus 2. No, plus 1. And then we will change this to a minus, this to a plus. Oh, that's fun. And let's just get rid of this x squared. Yeah. And then, no. Yeah. I'll put that at 2. Nope, no. Make it a minus. I just love experimenting with these things. They're just a lot of fun to experiment with. Let's make that a plus. No, make it a minus. And then I'll make that. Yeah, that one just looks fun. Look at that thing. This is a 5th-degree polynomial. It's just so weird in the way that it looks. Can I make this a 0.5? Holy crap. Yes, I can. Look at that thing. I can even do stuff like this. Check this out. I can do like x plus 1. Oop. X minus 2. X plus 3. X minus 4. X plus 5. Look at that. Just look at this graph right here. Look how insane that looks. But these are the types of polynomials that we are going to be dealing with. And they all follow a certain set of rules. Now, right now, my expectation for you, you should be scared. You should be. But I'm going to show you in a little bit why you shouldn't be. They look intimidating. They look crazy. They look menacing. They look like the type of thing that math has always warned you about. I'm going to get you beyond that. Don't you worry a little bit. So we're going to call this Intro to Polynomials. Today is the 10th. A linear equation is a polynomial. A quadratic equation is a polynomial. Cubic, quartic, quintic, they are all polynomials. You guys have used the prefix poly before. I know you have. In geometry, how did you use the word poly? In geometry, you had that prefix poly what? Oh, don't make me think that you forgot everything from geometry. What are shapes called in general? Oh, your geometry teacher should have told you. Oh, I'm going to save it. I'm going to save it. It's a polygon. Come on, you silly geometry kids. I didn't teach you geometry. A polynomial is an equation where all exponents are positive whole numbers. They are positive whole numbers. I'm going to show you where one doesn't kind of follow that rule in a little bit, but we'll get there. An example would be maybe y equals 2x plus 1, which is what we call linear. That is a polynomial. Y equals x squared plus x minus 6. This is a polynomial that we have referred to as quadratic. Or y equals x cubed plus x squared minus 3x plus 7. That is an example of what we would call a cubic. They are all polynomials. They are all polynomials. In this case, I would call this cubic, I would call it a third degree polynomial because, again, the largest exponent. A quadratic I would refer to as a second degree polynomial because of the exponent. A linear, a linear? I don't see an exponent on a linear. What's the largest exponent on a linear equation? I don't see anything there. What is it? Yeah, it's a first degree polynomial. But they're all polynomials, is my point. So whenever you hear that phrase, like a polynomial, like that's exactly what they're referring to. So let's start with a basic example, and let's see what we can do with them. Here's my first example. F of x equals 3x cubed minus 4x squared minus 17x plus 6. This is my first example that I would like to try. This is a higher degree polynomial. Third degree. It has an x cubed, an x squared, an x, blah, 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 blah. We could look at the graph if we wanted to, but I'll look at the graph in a little bit. Give me a number. Give me a number that's kind of smallish, but don't give me 1. Okay, let's try 2. I don't know, that's silly. Let's try 2. Here's what I would like to do. I would like to evaluate f of 2. I would like to evaluate f of 2. Now, when I say evaluate f of 2, I am referring to taking that value of 2 and plugging it in to that equation and seeing what happens. 2 is the input. I'm asking, what is the output? Well, logic dictates that we would take that 2 and we would shove it in for all of the variables in the equation, the x's specifically. And I don't really know what this is. I'm going to actually figure this out with you right here. Let's see. 3 parentheses 2 cubed minus 4 parentheses 2 squared. Parentheses will be your best friend. Make sure you use those parentheses correctly. And you can see right there on my calculator that I got a negative 20. Good for me. F of 2 is equal to negative 20. In fact, I can say that 2 comma negative 20 is a point on the graph. Excellent. Absolutely. Let's actually take a look at that. I'm going to bring up Desmos in a moment. So we can actually see that that ordered pair is indeed a point on the graph. Let's see. Desmos. Y equals, I'll do f of x. F of x equals 3x to the third power minus 4x to the second power minus 17x plus 6. Wow, look at that. That's pretty cool. All right, so hold on. Can I find 2? It won't give me 2. How about this? I do f of 2. Nope, f of 2. Will it give me that point on the graph? It won't give me the point on the graph because it's not one of those like important points or whatever. But in reality, it's about right there. It's 2 comma negative 20. And you can see it right here. I plugged in that 2 and it spit out a negative 20. That was kind of nice. Kind of did its thing. Huh. This thing actually crosses the x-axis at 3 different locations. I wonder if we can't figure out which one's which. Hold on. Let me zoom in. Zoom in, 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 zoom in. This one, Oh, look at that. Look at that. I don't know, I found that kind of interesting. We tried 2. I'm going to do negative 2. Let's do negative 2. Let's just see what happens with the negative 2. I'm going to take negative 2. I'm going to do the exact same thing that we just did. Oh, there are people talking. And he posts the notes at 33. Okay. He's asking if I can post the notes. All of the notes, just so you know, are coming out of my head. They're coming out of my head. So the notes, as we're taking them, you could always rewind the video and take a look at the notes. But otherwise, I do have hard copies. But anyway, back to this. Chapow! I want to plug in negative 2. I should probably bring the chat up over here. Let me bring the chat up over here so I can at least see what he's saying along with y'all. But boom. But let's actually do that. Let's plug in a negative 2. I want to evaluate f of negative 2. I'm going to do the exact same thing. I've said it from the beginning of the school year, and I'm going to say it again. Parentheses will save your life. Meaning, when you actually evaluate this on your own, you need to make sure that parentheses are doing what they should be doing, basically. There we go. I got the chat up finally. So when you actually type this thing out, I'm going to do this right here. Chapow! Let's see. 3 parentheses negative 2 cubed minus 4 parentheses negative 2 squared minus 17 parentheses negative 2 plus 6. Now, again, I'm going to zoom in on the calculator so you can see this here. I believe we know what the ordered pair is, but I just find it's important to see how I typed that in with the cubes and the squares and all that fun stuff. Chapow! And you can see that right there. There's my 0. Negative 2, comma 0. Negative 2, comma 0. I could say f of negative 2 is equal to 0. Negative 2, comma 0 is a point on the graph. Chapow! And I do see in the chat there, Joe. Like I said, in terms of the notes, after the fact, obviously you can go back and rewatch and see what kind of notes I put on there. I do have hard copies of these things. So if push comes to shove, if you do need to see like a hard copy or an electronic copy, send me an email. I can try to scan these for you. But I can't scan them now, obviously, because I'm teaching. So I'm about to show you a revolutionary new way. I am about to show you a revolutionary new way to do this. And it's something that we absolutely are going to be using throughout the course of this new unit. I just rewrote the exact same equation, and I did that on purpose. I want to evaluate f of 2. Now we know what f of 2 is. We did it before. F of 2 is negative 20. We know that. But watch this. This is something that maybe you've never seen before. Maybe you have seen it before. Good for you. It's called a bar. It's called a synthetic bar. And watch how I'm going to handle this. Those numbers that I just put on the inside of the bar represent the coefficients of the equation at the top of the page. 3x cubed, negative 4x squared, negative 17x, and a 6. I'm going to put this number on the outside. This number is the number you plug in. It's the number you plug in. In this case, we're taking a 2 and plugging it into the equation. Good for us. But now, it's supposed to, if I do this correctly, I should be getting a negative 20 in the end. Watch how this is going to be really messed up. This is a brand new thing that maybe you've never seen before. This is called a synthetic bar, and I'm showing you how to do something called synthetic substitution. Synthetic substitution. Here's what's going to happen in a moment. In a moment, when I start evaluating this bar, I am going to do a repeated series of steps that go back and forth between adding and multiplication. Adding and multiplication. It's going to keep going back and forth between adding and multiplication until I end up at the very end with negative 20. It's going to be amazing. That's all I'm going to do, though, is just adding and multiplication. Adding, in this case, is always done vertically. Adding is always done straight up and down, vertically. Multiplication will always happen against that number right there. Whatever this number is, the number that you're plugging in. Adding will be straight up and down. Multiplication will be against the number that you plugged in. Let's see how this works. First, I'm going to add 3 plus nothing. Well, that's anticlimactic. That's just a 3. Yay, yay. Okay, whatever. Shut up. I just added 3 to nothing. That's the worst possible. I don't know, whatever. But now I'm going to multiply. I'm going to multiply by that 2. 3 times 2 is 6. What do I do with the 6? I'm going to put the 6 in the first empty spot right there. 3 times 2 is 6. Yay. Then I'm going to repeat the steps. I'm going to add again. I'm going to add vertically. Negative 4 plus 6. 2. What number did I tell you we were going to end up with? It doesn't seem likely. What the heck, right? Let's just see what happens. Now that I've added, I got to go back to multiplication. So I'm going to multiply by that 2 on the outside again. And I get a 4. Now I'm going to go back to adding vertically. I'm going to add vertically. Okay. I don't believe it's going to work, Mr. Markey, but let's give it a shot. Negative 13. At this point, some of you are beginning to realize that I'm always right. I'm going to go back to multiplication. I'm going to multiply these two things together by the 2, and I get negative 26. And it's at this point that you all realize that I'm an evil genius. Because when I go back to adding one last time, 6 plus negative 26 gives you negative 20. This is the number you get back. This weird, strange thing called synthetic substitution works in such a way where you can put the coefficients of the equation across the top of the bar, the number that you're plugging in on the outside, and then you do nothing more than a repeated series of multiplication and addition. Let me move this up a little bit because I think I want to show this in a little more detail to those who are in the chat, because there's still that big ball of light in the middle of the screen. Hopefully that helped a little bit. So I would start with adding. 3 plus nothing is 3. Then I would multiply. 3 times 2 is 6. I put the 6 in the first empty spot. Then I would add vertically. Negative 4 plus 6 is 2. Then I would multiply against the number on the outside to get 4. Then I would add vertically to get negative 13. And then I would multiply by the number that's on the outside again to get negative 26. Then I would add vertically to get negative 20. The last number there is the number that you get back, the output. It is the output. It works in a lot of different ways. Let's try it again. Let's try it again with that other number that we tried. We tried it with a negative 2. So let's try it with a negative 2. I'm going to redraw my bar with 3, negative 4, negative 17, and 6. And I'm going to put a negative 2 on the outside. Take a moment. Literally take the next 15 seconds. Fill out the bar. Fill out the bar and get the correct answer on the bottom right. Do you remember, what did we get back? What did we get back when we plugged in a negative 2 the first time?
0.
We got 0. If you do it correctly, you should end up with a 0 as your last number. Give it a shot. Makes you feel good after you get it done. This is something called, as I said, this is called synthetic substitution. This is called synthetic substitution. I'm also going to refer to it as something else in a little bit, but we'll get there when we get there. 3 plus nothing is 3, multiplied by the negative 2. Add vertically, multiply by the negative 2. Be careful with your negatives and positives. Add vertically, multiply by the negative 2. Add vertically. That's how this thing works. And it is phenomenal. It is absolutely phenomenal. It really, really is. This strange looking thing. Ugh. I want to give you a definition. There's a few definitions that we have to go about with this, but I want to give you one of those definitions right here. So I'm going to put a little bullet point. The bullet point that I'm going to give you is this. If f of k is equal to 0, then k is a, quote, 0 of the function. If f of k is equal to 0, then k is what we call a 0 of the function. I put that 0 in quotes, of course, because another name for a 0 of the function is x-intercept, or root, or solution. They all mean the same thing. For this problem that we just did, we found out that f of negative 2 was equal to 0. Which means that, well, that negative 2, that number that you plugged in, is indeed a 0 of the function. And if you go back to the actual graph that I put up on the board right here, you can see that negative 2 is indeed an x-intercept. I could change this number right here to a negative 2, and you can see that that whole thing equals 0. It's a nice little point on the graph. Click. There we go. Can I change this color? No, I can't. I want to change it from blue. Nah, I'll have to do. Get back there. Yeah, we'll finish that later. Nice. So where am I going with this? Where am I going with this? Let me try a slightly different example. Let me flip that. There we go. And let's try a different example. New example. And this one we're going to stick with for a little bit. We're going to stick with this one for a little bit just to see what happens. Yeah, we'll stick with it for a little bit, but I have a different example I'm going to get to as well. F of x equals x cubed minus 6x squared plus 13x minus 10. Oh, yeah, absolutely. Let's see what we get here. Now, here's the thing. Let's say, for instance, that you are working on this problem, and you are responsible for solving this problem, for doing whatever it is that you have to do with this problem. Okay, cool. You all have graphing calculator capabilities on your Chromebooks. You don't need them right now. I'm going to show you what you need to see. But you all have graphing calculators available to you through the Chromebook. So if I'm doing this problem, I have no idea where to start, but I kind of do. Because what I would do instead of just panicking is I would go back to here and I would literally type in the equation. Let me zoom back out a little bit. There we go. Look at that. There's the graph in all of its wonderful glory. Yeah, I want to make that red. Hold on. I would really like to make it like red or something, a little bit more. Hold on. Yeah, there we go. Let's make it. There it is. It's red. It's better. Can you visibly identify where my graph crosses the x-axis? Can you guess where it crosses the x-axis? First of all, how many times does it cross the x-axis? Just once. Can you guess where? Where? Right there? What number? Take a guess. Let's see. Here's the thing. I can look at the graph all day long, but I can prove it. You say it looks like +2, right? Here's the thing. Go back to your notes. Hold on. Click. We believe 2 is an x-intercept. We believe that 2 is an x-intercept. All right, let's prove it. How do you prove it? Let's take a look. This number, as we said, is the number that we're plugging in. It is the possible 0. It is a possible 0. It's possible, but what we're about to do is going to prove it. Hey, what number do I put across the top here first? Second? There you go. It's a 1. Don't forget the 1 there. You need the 1 there. 1, -6, +13, -10. It's just the coefficients that you see in the equation in order from largest exponent to smallest exponent. We believe that 2 is an x-intercept. All right. Let's do synthetic division. 1, 2, -4, -8, +5, -10, a 0. Let me just recap again how I did that, just in case. Because at this point, you might feel pretty confident on it, and that's perfectly fine. I just want to make sure. You always start with adding 1 to, well, nothing, so it becomes a 1. Then you multiply. 1 times 2 is 2. Then you add vertically to get -4. Then you multiply by that 2 to get -8. Then you add vertically to get +5. And then you multiply by the 2 to get, oh, that should have been +10. I'll fix it to a +10 in a moment. Because I knew that when you added the two of them together, you got 0. Let me change that to a +10. Cha-ta! There we go. This right here, that number, this proves x equals 2 is a 0 of the function. It proves it. Getting that 0 at the end of synthetic substitution proves that whatever number you plugged in is a 0 of the function. It's really phenomenal. This method of getting these numbers is going to be a lot faster and a lot more efficient than anything that we've ever done in the past. It's going to be amazing. For me, not for you, but for me. It really is. I got to take it a little step farther, though. This 0 at the end means so much more. It means so much more. Come on, paper. I gave you an if-then statement earlier. Let me give you another if-then statement. Bullet point. If. How did we get 2? Oh, good question. Okay. So in the chat, he's asking how we got 2. And I'm assuming he means this 2 right here. How did we get that 2? Well, Joe, I'm going to tell you what I'm going to tell them, and this is very important. How do we determine the number that's on the outside right here? Literally, look at the graph. Visually identify any zeros that you can, and then plug them into the synthetic substitution. I'll show you what it looks like on the calculator. Here, watch this. On the calculator, x to the third minus 6x squared plus 13x minus 10. If I were to zoom in right here, let it focus for a moment. There it is. There's my equation, the exact equation that we've been dealing with. I'm going to graph it. Shaha! I don't really know what that number is. It could be any number. I mean, it could be like 2, maybe it's like 2 and change. I don't know. There's more than one way to know. But one of the best ways to be like, okay, is it 2? Is it 3? Is it 2.5? Do this. If you show the synthetic substitution and you get that 0, you have proven that that number is a 0 of the function. That's what this does. That's why this synthetic substitution is so important. By the way, I haven't even shown you the most important part yet. I have not shown you the most important part yet, but we'll get there.
What if there's no graph?
What do you mean if there's no graph? If you just have the equation? Do you have a graphing calculator on your Chromebook? There you go. I'm not even kidding. Literally, just look at the graph. Type it in. See what happens. Now, sometimes you might be faced with a scenario where the graph is like off the screen. You know what I'm saying? Like when you actually do this, the graph doesn't show up in the window because the graph is actually like over here somewhere. In those instances, there is a possibility of a little bit of guess and check action going on, but those examples are going to be few and far between for the Algebra 2 CP class. Okay, there is a more advanced method that is taught, but that advanced method is typically saved for those dumb honors kids, the ones that we're going to beat up. You don't want to beat them up? Fine. All right. Who's with me? Oh, everyone's like, nope, I'm going to check my phone. Whatever. Did I tell you the freshman story? All right. I was teaching Algebra 2 one year. It was CP, and there were some kids running through the hallway. I thought I told you this story. Anyway, the kids ran through the hallway, and I'm like, stupid freshmen. And then the other kids in the class who were all like 10th, 11th, 12th graders are like, yeah, freshmen are so dumb, blah, 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 blah. And I'm like, yeah. And I took it a step farther. I'm just like, listen, let's just all go out in the hallway right now. Let's go find a freshman. Let's go start beating them up. And they're like, yeah, let's get those freshmen. Yeah. Meanwhile, there's one kid in the corner of the room who's a freshman. And without skipping a beat, he's like, yeah, guys, let's get him. That's awesome. I knew he was a freshman. I wanted to see what he would say. Okay, back to this. Sorry, I'm reading the chat. If f of k is equal to 0, which again, I gave you a statement like this earlier, but I want to go a step farther. If f of k is equal to 0, then x minus k is a factor of f of x. If f of k is equal to 0, then I'm going to take it a step farther. Then x minus k is a factor. Let's see how that plays out. Let's see how that plays out, actually. Supposedly, it's going to be a factor. Let me give you a quadratic. Let's just do a basic quadratic right here. Let's try example f of x equals x squared plus 7x plus 12. Something very basic like that. Now, I'm going to go to my graphing calculator, and I'm going to type in the equation that I have there. Ooh, I got an email. I don't care about that. Cool. And I'm going to zoom in and show you what this thing looks like. So there is my equation. Graph. Ooh. Let me change the window a little bit. Let's go from like -10 to 0. Well, let's go from -5 to 5. Boom, let's look at this graph. All right. Let's go from -2. Let's go from -5. There we go. Let's look at this graph. All right. Where do you think it crosses? -3 and -4. It looks like -3 and -4, right? It looks, and I agree, that, look what's up here, -3, look at it blinking, -3, it works, and -4, yes, they look like the zeros of the function, and they are, but let's prove it using stuff that we've done. Now check this out, this is going to be really insane. Let me put something extra on the board real quick. Let me just put something a little bit extra on the board right over here. Just for the sake of argument, I'm going to return to this in a moment. But would you agree that that's what it factors into? 3 times 4, 3 plus 4. It works. It does. In fact, if I were to solve this, I would get x equals -3 and x equals -4. I just want to point that out for a moment, and I'm going to come back to that in a moment because I'm about to blow your minds wide open. Check this out. Let's try the -3. I'm going to do a little synthetic division right here. I'm going to put a 1, a 7, and a 12 because those are the coefficients. It's a 1x squared, a 7x, and a 12. And I'm going to put the -3 on the outside. That's the number that I want to plug in. And let's go through and see if the -3 is indeed a 0. There's the 1, the -3, and the 4, and the -12, and the 0. Yeah! So this number proves -3 is a, quote, 0. And if I go to the definition that I have at the top of the board, it proves that x plus 3 is a factor. It proves that x plus 3 is indeed a factor. because it says x minus k, and if you did x minus -3, it would become x plus 3. Does anybody see what I see? There's something strange going on the board right now. There's something strange going on the board right now. Give me two numbers that multiply to 24. Give me two numbers that multiply to 24. 6 and 4. Okay. 6 and 4 multiplied give you 24. I agree. What is 24 divided by 6? Yeah, 4. So you said 6 times 4 give you 24. If I did 24 divided by 6, it gave you the other number. What if I did 24 divided by 4? It gave you the 6. There's something strange going on here. What I just explained, you're going to be like, why is he even asking me this? You'll find out in a minute. We just took this quadratic and we actually performed something known as synthetic division. We call it synthetic division. And what I actually did was I took this quadratic and I divided it by this factor. I divided it by this factor. What two factors multiply to give you this quadratic? X plus 3 and what? What multiplies to give you this? X plus 3 and something else. X plus 4. Multiplied together, they give you this quadratic. I agree wholeheartedly. What I just did was synthetic division. Did anybody notice these numbers right here? These two numbers are not a coincidence. These two numbers mean everything in the world. Let me go into a little bit more detail. This is going to be insane. Should have seen me on election night. I was in my glory. It's all about mathematics. Okay, check this out. First of all, x squared plus 7x plus 12 divided by x plus 3 equals x plus 4. I'm about to show you how to do division with polynomials. You ever do long division back in the day? Yeah. I don't really teach long division of polynomials. There is a way to do long division with polynomials, but I don't teach it. Because you could just do this. Well, again, to be fair, I do teach it to the higher levels, but shut up. Check this out. This is the same as the following. This is the same as the following. It's the exact same thing. This is the factor x plus 3. That -3 is the factor x plus 3. This number right here, when you divide stuff, what do you call stuff that's left over when you do division? Yeah, this is your remainder. That's your remainder. This number represents the constant, and this number represents your x term. So in reality, the result of division is 1x plus 4. This is insane. This is legitimately insane. I have one more example that I want to show you that's going to deep dive this one more time. I want to show you a slightly different example. But this is your first day seeing this synthetic bar. And I showed you generally how it works in terms of the adding and the multiplying and the adding and the multiplying. But this bar means so much more than you could ever imagine. So much more. Hold up. Let's try one more example. But this example is going to pretty much take us to the end of it. It's going to be amazing. Let's try this. Example, divide, parentheses, x cubed plus 2x squared minus 5x minus 6 divided by x minus 2. As I said, it is the same exact thing as this. It is the same exact thing as this. Now remember, if x minus 2 is a factor, that means that the 0 in question is positive 2. That is a very important distinction to make. The numbers in the synthetic bar are the original polynomial that you're trying to divide. In this case, it's a 1x cubed, 2x squared, negative 5x, negative 6. And I'm going to run through this synthetic division. If I run through this synthetic division, 1, 2, 4, 8, 3, positive 6, 0, getting that 0 at the end proves that 2 is a 0 of the function, and x minus 2 is a factor of the function. But not only that, this is my, as I said before, my remainder. This number is my constant. This number is my x term. Take a wild guess. What do you think this number represents? If this is my constant and then my x, what comes next? I know you want to say it. If you went up 1 degree from a regular x, what do you have? Take a guess. Be brave. No one wants to say it. My heart's broken in a million pieces. I'm going to write it and people are going to be like, oh yeah, I knew that. It's your x squared term. The more numbers you have on the bottom, the more it would go up in degrees. In reality, the result is a 1x squared plus 4x plus 3. Now, I want to show you something. I want to show you something that's really going to mess with your heads a little bit. I mean, not that I've already messed with your heads a bunch, but I'm going to show you how this thing actually works in a bit more deeper context. So let me go to my calculator real quick. Zooming in, zooming in, zooming in, zooming in, zooming in. Here we go. Let me put in an x cubed plus 2x squared minus 5x minus 6. Okay. Watch with your eyes. Watch with your eyes. Graph. Oh, hold on. Zoom 6. There we go. Here's my original function. My original function. I'm gonna. Ow! I hit my leg. I'm gonna go up to the board. I'm gonna mark these. Now I created this one on purpose. This is your x equals 2 solution, or your x minus 2 factor. This is your x equals negative 1 solution, or your x plus 1 factor. This is your x equals negative 3 solution, or your x plus 3 factor. Those what those 3 zeros really mean. Watch with your eyes. Watch with your eyes. I'm about to divide this function by x minus 2. I put it in parentheses, mind you. But I'm about to divide this function by x minus 2. I'm dividing out a factor. Remember I said 24 before? If you take 24 and you divide it by 6, you are literally ripping out the 6. And what's left over when you take 24 divided by 6? 4. That's what's left over. Now, if I divide this function by x minus 2, get rid of this, there we go. There's going to be something left over. But watch what's left over. Graph. Tell me something about what's left over. Tell me what is so interesting about what's left over. Ooh, the x-intercepts. They're the same. The x-intercepts are the same. This one, I divided it out. It's gone. I've ripped it from existence. I've divided it. But these two are still there. They're still there. In fact, these two factors, if you combined these two factors and multiplied them together, you would end up with that quadratic. Pick a number, -1 or -3. Pick one. -3. I'm going to divide that one out next. Let's just see what happens. I'm going to divide out the x minus 3. Or I'm sorry, the -3. Whatever. Watch this, watch this, watch this. Divided by x minus 3. Now I'm ripping out the next term. Oh, that would have ruined everything. It would have. Good catch. Watch what's going to happen. Graph. We divided out the x minus 2. We divided out the x plus 3. And the only thing left over was the x plus 1, which is a linear function. It's a linear function. This is really insane. This is really insane. Watch this. I'm going to type in the following. By the way, you know, when I was in high school, when I was in like algebra 2 and trigonometry, I'm going to be completely honest with you. When I took high school algebra 2 and high school trigonometry, I got straight A's. I slept in class all the time. I was that kid that you absolutely hated because he slept and never paid attention, but I got everything right. You know what I'm talking about? Yeah, I was that kid, okay? So what I would do when I was bored in class and I wasn't paying attention, I would mess around with the graphing calculator. I would just mess around with it, just for fun. Check this out. I'm going to do x plus 1 and x minus 2. I'm going to type in those two terms right there. And what I suspect is going to happen is I'm going to get a quadratic. I'm going to get a quadratic that goes through just those 2 points and not this third one right here, just for funsies. Graph. Jaboom, jaboom. And it works perfectly. Then I can put in that last term if I wanted to. I put in that last term if I want to, where I multiply the third one in, and it goes right back to normal, going through those 3 zeros. Ladies and gentlemen, everything that I have shown you today is going to intermix with itself. Because eventually, we're going to come to a problem like this, and I want you to write this down. It's the last thing I'm going to have you write down today. It is the example that we have been working on pretty much all class period. Where in the heck is that Sharpie? Did someone steal it? Is it in my pocket? Did I throw it? I throw things all the time. I really don't have any idea. All right, back to this. Aha! So eventually, I'm going to give you the following example, where I say, factor completely. I'm going to say factor completely, and I'm going to give you the example of x cubed plus 2x squared minus 5x minus 6. This is the example that I gave you before. This is the exact problem. Could have sworn I threw it somewhere. Whatever. Then eventually, after some synthetic work, you'd end up with the following answer. X minus 2, x plus 1, x plus 3, in which you can identify the zeros, you can identify the factors, you can show me exactly how you got there. It is going to be phenomenal. This is just day one. On Monday, we're going to get back into this with a larger class. I'm so excited. Anyway, that's my time. There's the bell. See you then. I have no idea where that marker went, by the way. And I'm a little upset. It was my favorite marker. It really wasn't. I just picked it up this morning. I should really end that live stream. Oh my God. Thank you. Did you know it was